So, when did humans lose all their body hair? The simple answer is, we never did. Just look at your arms, your legs, your head. There's still hair there. The real question is a bit different. When did our ancestors lose their thick coat of fur, the kind you see on a chimpanzee? That question is a lot more interesting, and the answer isn't a single date on a calendar. It was a long, slow process. It happened over thousands of generations. It was a trade off, a deal our ancestors made with the environment. They gave up their fur coat. In return, they got something amazing. They got the ability to run. And that changed everything. To understand how we lost our fur, we have to go back in time. Right, way back. Think 3 or 4 million years ago. Our ancestors then were not quite human yet. They were hominins like Australopithecus. Lucy was one of them. They lived in Africa. And they were hairy, very hairy. Their world was changing. The dense forests where their ape-like ancestors lived were shrinking. The land was opening up, turning into vast savanna. Think grasslands dotted with trees. This new environment presented a huge problem and a huge opportunity. In the forest, being hairy is a pretty good deal. You're mostly in the shade. The fur protects you from scrapes and insects. It helps you keep warm when it gets cool. It offers camouflage. A chimp's dark fur blends into the shadows of the forest canopy. For our early hairy ancestors, fur was a useful tool. It was their all-purpose, built-in outerwear. But then they started spending more time out of the trees. They started walking on two legs, becoming bipedal. This was a massive shift. It freed up their hands to carry things, to make tools. It also exposed them to the full, brutal force of the African sun. A hairy animal walking upright on the savanna at noon is getting baked. The sun is directly overhead. It beats down on the head and shoulders. A thick coat of fur under that sun becomes a furnace. It traps heat. It makes it almost impossible to stay active during the hottest parts of the day. This is where the first big pressure to lose fur came from. It was all about staying cool. It was a problem of thermoregulation. Our bodies, like any engine, produce heat when they work. To keep from overheating, you have to get rid of that heat. For a furry animal, the main way to do this is to pant. A dog pants, a lion pants. It works, but it's not very efficient, and you can't really pant effectively while you're running for your life or chasing down a meal. Our ancestors found a different solution, a better one. They started to sweat. Us humans are the sweatiest apes by a long shot. We are covered in millions of tiny eccrine sweat glands. When we get hot, these glands release a salty water onto our skin. As that water evaporates, it takes heat with it. It's like a personal, full-body air conditioning system. It is incredibly effective. It's what allows a marathon runner to run for hours in the heat without dying of heat stroke. But there's a catch. This evaporative cooling system works best on bare skin. Imagine trying to sweat with a fur coat on. The sweat would just get trapped in the fur. It would become a damp, matted mess. It wouldn't evaporate well. The cooling effect would be minimal. So for our amazing sweat-based cooling system to work, the fur had to go. Less fur meant more efficient cooling. More efficient cooling meant you could be active for longer during the day. This gave our ancestors a huge advantage. On the savanna, most of the big predators like lions are lazy during the midday heat. They rest in the shade. They can't handle the sun, but a naked, sweating hominin. They could go out and scavenge for food when their competitors were all asleep. They could track animals over long distances without overheating. This is the idea behind endurance running. Some scientists believe our ancestors evolved to be long-distance runners. Not fast sprinters, but persistent hunters who could chase an animal for miles and miles under the hot sun until the animal collapsed from heat exhaustion. You can't do that if you're covered in fur. You need bare skin and a whole lot of sweat. So the main driver was a change in environment and a change in behavior, moving from the shady forest to the open savanna. Moving from climbing trees to walking and running on the ground, this need to stay cool, to shed heat, was probably the most powerful force pushing us toward nakedness. But there were other factors too. Another big one was parasites. Fur is a wonderful home for parasites. Ticks, lice, fleas, and all sorts of other nasty critters love to live in a warm, dense coat of hair. These parasites aren't just annoying. They carry diseases. They can make you sick, weak, and even kill you. An animal with a heavy parasite load is not a healthy animal. It's not going to be a very successful parent. By losing our fur, we kicked all those tenants out. A smooth-skinned hominin was a much less inviting target for these parasites. They had fewer places to hide, fewer places to lay their eggs. This would have made our ancestors healthier. Healthier individuals are more likely to survive and have kids, and they are more attractive to potential mates. This leads to another possible reason for our hairlessness: sexual selection. It's possible that once the process of losing hair began, smooth skin became a desirable trait. Why? Because smooth skin is a billboard for health. On a hairy ape, you can't easily see skin infections, rashes, or the bites of parasites. On a naked ape, it's all out in the open. Clear, smooth skin signals that you are healthy and free of disease. It's an honest signal. You can't fake it. So, our ancestors might have started to find less hairy partners more attractive. Over many generations, this preference would have pushed the population towards less and less hair. The individuals with smoother skin got to have more babies, and they passed on their less hairy genes. So we have a few strong theories. The need to stay cool while running on the savanna is the big one. The need to get rid of parasites is another, and the possibility that we found smooth skin attractive adds another layer. These ideas are not mutually exclusive, they probably all work together, pushing our evolution in the same direction. That covers the why. But what about the when? This is harder to pin down, hair doesn't fossilize. We can't just dig up an ancient skeleton and check to see if it was hairy. So scientists have to get clever. They have to look for indirect evidence, and they've found it in some really interesting places. One of the best clues comes from our skin color. If you take away an ape's fur, you'll find that underneath, their skin is quite pale. Our early hairy ancestors probably had pale skin too. Fur does a great job of blocking the sun's ultraviolet, or UV, radiation. It's a natural sunblock. Once we lost that furry protection, our skin was suddenly exposed to the intense African sun. UV radiation is dangerous. Too much of it can damage a vital nutrient in our bodies called folate. Folate is crucial for healthy fetal development. If a pregnant mother has low folate levels, her baby is at high risk for serious birth defects of the brain and spinal cord, like spina bifida. This is a huge evolutionary problem. Any trait that leads to birth defects is going to be strongly selected against. The body's natural defense against UV radiation is a pigment called melanin. It's the stuff that makes skin dark. Melanin is an amazing natural sunscreen. It absorbs UV radiation and prevents it from penetrating deeper into the skin and destroying folate. So, as soon as we lost our fur, there would have been immense pressure to develop dark skin. The individuals with slightly darker skin would have had healthier babies. Their genes would have spread. Over time, our ancestors evolved permanently dark skin to protect themselves. Scientists can actually look at the genes that control skin color. There's a key gene called MC1R. By studying the DNA of people from all around the world, geneticists have figured out that the specific version of the MC1R gene that produces dark skin in African populations became standard in the human lineage around 1.2 million years ago. This gives us a really solid clue. If our ancestors needed dark skin to protect them from the sun around 1.2 million years ago, it's a pretty good bet that this is around the time they had lost their fur. The evolution of the solution dark skin tells us when the problem no fur appeared. This time frame, a little over 1 million years ago, lines up perfectly with a hominin species called Homo erectus. These ancestors were taller and had longer legs than Australopithecus. Their bodies were built for walking and running long distances. They were spreading out across the landscape, living a much more active, exposed lifestyle. It makes perfect sense that this was the ancestor who shed their fur and evolved the body of a master endurance runner. There's another, even stranger, piece of evidence. It comes from lice. Humans are special. We are the only primate that hosts two different kinds of lice. We have head lice, which live in the hair on our heads. And we have pubic lice, which live in our pubic hair. They are different species. Genetically, the human pubic louse is most closely related to the louse that lives on gorillas. This suggests that at some point, one of our ancestors picked up lice from a gorilla. It's weird to think about, but it probably happened from sleeping in a nest a gorilla had used, or maybe even from butchering and eating one. But the really interesting part is the head louse. The human head louse is our own personal ancient companion. It evolved with us from the lice that lived on our chimpanzee-like ancestors. Now, here's the clever bit. For a chimp, there is no difference between head hair and body hair. It's all one continuous forest of fur. A louse can crawl from a chimp's head to its back to its leg without any problem. But, on a modern human, the hair on the head is separated from the hair in the pubic region by a vast hairless desert of skin. A head louse can't survive that journey. The two areas are completely isolated. Scientists figured that head lice and pubic lice must have become two separate populations because the loss of our body hair created this barrier between them. They could no longer interbreed. So, if we could figure out when the two types of lice diverged, it would tell us when that hairless barrier appeared. Using a technique called a molecular clock, which compares the genetic differences between species to estimate how long ago they shared a common ancestor, scientists studied the DNA of lice. The results are still debated, but some studies suggest that head and pubic lice parted ways around 3 million years ago. This is much earlier than the skin color evidence suggests. It might mean that the process of losing our body hair started much earlier, perhaps with Australopithecus, and happened in stages. Maybe the hair on our torsos and limbs thinned out first, creating the initial barrier for lice, and then the full naked skinned, sweaty runner package came together later with Homo erectus. Evolution is often a messy, gradual process, not a sudden switch. It's likely that our ancestors went through a long, patchy-haired, awkward phase. So the best guess is that the process started over 2 million years ago, but the job was largely finished by about 1.2 million years ago with Homo erectus. They were the first of our ancestors to look, at least from a distance, recognizably human in their body shape, tall, long-legged, and naked. Losing our fur was a great deal, but it came with consequences. It was a trade-off. We gained a superb cooling system, but we lost our insulation. We were now great at handling the heat of the day, but what about the cold of the night? Or what about when we moved out of Africa into colder climates? A naked ape in a cold place has a serious problem. This problem probably drove some other huge innovations in human evolution. One was almost certainly the control of fire. A fire provides warmth. It replaces the function of a fur coat. For a naked species, being able to make and control fire is a game changer. It allows you to survive cold nights. It allows you to expand into colder regions. The archaeological evidence for the controlled use of fire gets much more reliable around the time of Homo erectus. It seems likely that our nakedness and our mastery of fire are linked. The other solution, of course, was clothing. At first, this was probably just animal skins draped over the body for warmth. Over time, we got better at it. We learned to scrape and prepare hides. We invented needles made of bone to sew them together into fitted garments. Our clothing became our artificial, removable fur. It's much more versatile than a real fur coat. You can put it on when it's cold and take it off when it's hot. This adaptability allowed us to live almost anywhere on the planet, from the hottest deserts to the frozen Arctic. Our nakedness, in a way, forced us to become smarter, to become inventors, to solve problems with technology rather than just biology. Which brings us back to the first point. We didn't lose all our hair, we kept some of it. And the places where we kept it are just as interesting as the places where we lost it. Why did we keep the hair on our heads? The answer goes back to the savanna sun. When we started walking upright, our head became the part of our body most consistently exposed to the sun. Having a thick mat of hair on the scalp acts like a built-in hat. It shields the skull and the delicate brain inside from solar radiation. It creates a layer of air between the skin and the hot hair surface, helping to keep the brain from overheating. It's a vital piece of personal equipment. What about eyebrows? They seem pretty useless. But try running on a hot day. Sweat pours down your forehead. Eyebrows are perfectly shaped to catch that sweat and channel it away to the sides of your face, keeping the salty sting out of your eyes. They are sweatbands designed by evolution. Eyelashes do a similar job, keeping dust and debris out of our sensitive eyes. And then there's the hair in our armpits and our pubic region. This hair is different from the hair on our head. It's thicker, coarser, and it only grows in at puberty. This is a clue to its function. These areas are also home to special sweat glands called apocrine glands, which release an oily sweat full of chemical compounds. And bacteria on the skin break these compounds down, producing body odor. The hair in these regions acts as a wick. It traps these scent molecules and disperses them into the air. In the animal world, scent is a huge part of communication. These scents signal sexual maturity. They are our own personal pheromones. So, pubic and armpit hair are likely there for scent-based communication, a leftover from a more primitive animal past. They might also reduce friction in areas where skin rubs against skin. The story of how we lost our fur is the story of how we became human. It wasn't a single event. It was a long, slow adaptation to a changing world. We traded our coat for a cooling system. That trade-off allowed us to become endurance athletes on the hot savanna. It made us healthier by ditching parasites. It might have even changed who we found attractive. But it also left us vulnerable. It left us cold and exposed to the sun. To solve those new problems, we had to get smarter. We had to master fire. We had to invent clothing. We had to use our big brains to create cultural and technological solutions to biological problems. When we look at our own smooth skin, we're not seeing a sign of weakness or fragility. We're seeing the result of a profound evolutionary shift. We're looking at the skin of a long distance runner, the skin of a clever survivor, the skin that carries the genetic history of our journey out of the trees and across the world. We are the naked ape, and we got this way not by accident, but because being naked was, for our ancestors, the key to survival. It's one of the most important things that makes us who we are. It's a story written not in stone, but on our own skin.